Hey everyone, how's everyone doing? How was the exam for you guys? What did y'all think? Quite a bit tougher than the other exams, I take it. Yeah. Yeah. That is how it usually goes. It is so it usually starts off pretty easy. Second's a little tougher. The third's where it starts getting tough, and then the final is even tougher. So be warned. Yeah, you felt like the review is useless, really. Ow, man. Sorry to hear that. Huh. Yeah. Like the applications are all pretty much the same. I think that was because like for the applications, it's basically just integrating a density, and everything on the exam had to do with integration to begin with. So it's just basically set up this integral, figure out the coordinate system, that kind of thing. Yeah. Yeah. Yeah, I specifically at the end of the extra lecture, because I saw that question on the exam, I was like, yeah, I should probably address this directly. So yeah, I made sure to cover that specifically because I knew that was on the exam. Yep. Alrighty. So today we are starting to talk about the stuff that's going to carry us through the end of the semester, the end material. Going to talk about vector fields, and most of the remainder of the material is going to be integrating vector fields in various ways, and then some integral theorems involving vector fields and scalar fields also, but yeah. Okay. So in the syllabus, we talk about change, or it says recovering change of variables. In the past, that's always been optional, and it's never shown up on an exam directly. We've done change of variables when we talk about changing coordinate systems and that kind of thing, but we haven't talked about what's going on behind it. If I get a hint that something like that is going to show up on the final, then I will make sure to cover it later. But honestly, I'm gonna skip it for now, and it should be safe to do so. And if it's not, then we'll come back and cover it later. But yeah, I don't think we need to cover change of variables. Okay, so today we're going to talk about one more kind of function, vector fields. So hang on, let me, not directly, shouldn't have been, unless you're talking about it, there shouldn't have been any abstract like change of variables questions other than cylindrical and spherical type things. Trying to think what you'd be referring to. Hang on, let me. No, no, nothing. So that's not what we mean by change of variables. Change of variables basically means switch to a different coordinate system, essentially, is what that means. That's just switching the order of integration. Yeah. And we've covered that before. Yeah. Okay. All right. So vector fields. So consider a function which I don't need to phrase it like this. Let me just give the definition of vector field and give some examples. So a vector field is a function which assigns, so let me say a vector field on R3. We'll have vector fields on R2 also. So the function which assigns to each point in the domain so to each point x, y, z, it assigns a vector, capital F, vector over it, arrow over it, of x, y, z. So basically, we're in R3, and for each point in the domain, this function is going to assign a vector to that point. So it's going to assign, a three-dimensional vector. So F1, F2, F3. Each component is a function, depending on the point x, y, z, is a function of three variables. So at each point, we're assigning a vector, a three-dimensional vector. So for a vector field on R3, for every point in the domain in R3, we assign a three-dimensional vector. For a vector field on R2, same thing. To each point in the domain, x, y, we assign a two-dimensional vector, F1, F2, depending on the point x, y. Okay, so functions of three variables before, to each point in the domain in R3, we would, the function would spit out a number. It would assign a number to each point. Now, at each point, we're assigning a vector. So an example, most of the physical examples of this are like fields of some sort, force fields, etc. So So for example, wind velocity, right? So if you look at an area, you put it in a coordinate system in R2 in the plane. At each point, you can assign the wind velocity. You can look at the wind velocity at a given point, right? Velocity is a vector. So at each point, this will tell you the wind velocity at that point, right? It'll give you some vector. So force fields are another very common example. And we're not talking about like sci-fi force fields, right? We're talking about, oh my goodness, the doggo's going nuts. So we're talking about like so force is going to be a vector, right? So for instance, gravitational force. So if you pick any point around here, the gravitational force is basically going to be just your constant negative 9.8 newtons, et cetera. Oh, sorry, whatever the constant is, I've already forgotten. But it's basically a constant vector pointing straight down. So basically, to each point, you assign a constant vector according to whatever, whose magnitude, pointing straight down, whose magnitude is whatever the gravitational force is, the magnitude of that. So gravitational force, magnetic force field, etc. So just think a lot of vectors. At every point, there's a vector assigned by this function. And the way we write these is we write them in component form. So we write them as vectors, and each component is a function of however many variables we're dealing with. If we're in R3, each component's a function of 3 variables. So each component depends on the point. And if we're in R2, each component is a function of 2 variables. So for example, yeah, let me just write that down. Okay. So we can kind of use a shorthand, get rid of the X, Y, Z, and whatever. But our vector field F, the component functions, each of these guys are the component functions. F1, F2, and F3. Or if we're on R2, F1, F2. And capital F is our vector field. Okay. So for example, suppose our vector field is y minus x, nope, sorry, z minus y. xy, nope, sorry, that's y minus x. It really doesn't, y minus z. Literally doesn't matter, whatever. Xy, and say z to the 4. Suppose this is our vector field on R3. What is the value of the vector field at the point 242? Easy enough. So we're at the point 242. So x is 2, y is 4, z is 2. The value of a vector field. So at each point at the point 242, we get a 3-dimensional vector. So we just get y minus z for the first component, which is 4 minus 2. That's 2. Xy, which is 2 times 4. That's 8. And z to the 4, which is 2 to the 4. Right, exactly. 16. Wait, hang on. No. Right, y minus z. Yeah, is our 2. Yep. Very simple. But this is what our vector fields look like. It's just a vector and each component's a function. Okay. So vector fields to literally every single point in the domain, infinitely many of these points, we're assigning a vector. Obviously, you would not be able to tell what's going on if, and no computer would be able to actually render an actual representation of a vector field visually, right? Like you can't plug in a vector at every single point and have any idea what's going on. And no computer could do that anyways. But we can sketch a vector field by just picking sort of a lattice of points, right? So just taking like x 0, 1, 2, 3, y 0, 1, 2, 3, etc. And in each of those points, plugging in the point into the function and seeing what vector you get and plotting that vector at that point. So plotting a few of those points, select points, you can get an idea what's going on with the vector field. We're not going to do this too often, but it's helpful to be able to look at a vector field and recognize what's going on. So for example, let's sketch the vector field on R2. F of xy is negative yx. So what we're going to do is we're just going to pick certain points, plug them in, and see what vector we get, and then plot that vector. Et cetera, et cetera. Okay. Let me write it like this. Okay, so let's just pick some points. We don't need to be exhaustive here. And see what vector we get, and then plot it at that point. So yeah, we plot each vector at a point as starting at that point. So at 0, 0, obviously we plug that into our vector field. The first component is negative y, which is 0. The second is x, which is 0. So at the origin, we get the 0 vector, which you can just represent as like a point. Okay, how about at 1, 0? What is f of 1, 0? What vector do we get?
Isn't it just 0, 1?
Right. So the first component is x, which is 0. And the second component, or sorry, negative y, which is 0. Sorry. And the second component is x, which is 1 in this case. And then at 0, 1, our vector field, the first component's negative y, which is negative 1. Second component is x, which is 0. Sorry, let me plot these. So at 1, 0, we get the vector 0, 1. So starting at 1, 0, we get the vector which goes 0 in the x direction, 1 in the y direction. That's our 0, 1. At negative 1, 0, at the point 0, 1, so at the point 0, 1 up here, we get the vector negative 1, 0. So the vector which goes negative 1 in the x direction, 0 in the y direction. Whoops, that's this guy. And then continuing, at negative 1, 0, negative y is 0, x is negative 1. So negative 1, 0, we get the vector which goes negative 0 in the x direction, negative 1 in the y direction. And at 0, negative 1, negative y is negative negative 1, which is 1, and x is 0. So 0, negative 1, we get the vector going 1 in the x direction, 0 in the y direction. And then we can plot some other points. So let's say like 1, 1. Negative y is going to be negative 1. X is going to be 1. So at the point 1, 1, we get the vector going negative 1 in the y direction, and the x direction, sorry, 1 in the y direction. So negative 1, 1. And then we can repeat this. We see we get something like this. And essentially, the further away from the origin you get, the bigger the magnitude of our vector. And it's always going around counterclockwise. So it's basically going to lie on the circle. Centered at the origin, and will be tangent to it. Etc. So that's what our vector field is going to be. That's just a sketch of it, but I don't want to dwell too long on that. Pretty easy to sketch it. Okay, any questions about vector fields so far? Okay. All right. So let's look at some operations we're going to be doing on vector fields. So the main thing we're going to be dealing with is going to be involving something we've sort of already seen before. Should look familiar. It's going to be the del operator. So it's going to be the del, like in gradient. We'll see how we can interpret the gradient now, thinking of it as the del operator. So the del operator is just going to be a vector. So the first component is partial with respect to x. The second is partial with respect to y. The third is partial with respect to v. If we're dealing with vector fields on R3, and if we're dealing with vector fields on R2, then it's just partial with respect to x, partial with respect to y. Okay, so del, we're going to think of as like differentiation, but it's going to be a vector. It's going to have components, and each of those components is going to do be a partial derivative. So don't think of this like an actual vector. Like the vector algebra is going to work out like a vector, but it's not going to have like you won't be able to plot this vector, right? But it's helpful to think of it as a vector because we're going to do like vector algebra, and the operations we're going to follow all the same rules of vector algebra we already know. So for example, and let me say this. So when we multiply a function, a scalar function, so say ddx, ddy, or ddz, these components, so just dd whatever, that can stand in for x, y, or z. So when we multiply a component by a scalar function, f, it means differentiate according to whatever the partial is. So differentiation. Multiplication by that ddx is differentiation by x, in other words. So ddx times f is going to be the partial of f with respect to x. We're going to be doing the usual vector functions, vector algebra. And when we multiply one of these components of del by a function, then we're just performing that derivative on the scalar function. This will make more sense when we do a couple examples. So we've already seen the gradient of f. So f is a scalar function. Say it's a function of 3 variables. Write that. And we saw that we write it as del of f. So in this sense, so if we think of del as a vector, ddx, ddy, ddz, and f is a scalar, so del's our vector operator, but just think of it like a vector. F is going to be a scalar. It's a function, but treat it like a scalar for the purposes of vector algebra. When you multiply a vector by a scalar, you just multiply each component by that scalar. So we get ddx times f, ddy times f, ddz times f. And we said when you multiply a function by the operator ddx, then it's just the differentiation. So we get df dx, df dy, df dz. And that was our gradient. Remember, as a vector, each component is the partial derivative of the function we're taking the gradient of. So just think of it like the vector del times the scalar function f. Multiply each component by f, and then multiplying d dx by f means take the partial of f with respect to x, so on and so forth. So that's one thing we know how to do with vectors, is multiply them by scalars, scalar functions in this case. Well, we also saw a couple other things we can do with vectors. We can multiply them. We can take dot product of two vectors. So for instance, what happens when we do that? If we dot a del with a vector field now, so a function which is a vector. So what we get is the divergence of that vector field. So if we have a vector field, F, so in R3, the component functions are F1, F2, F3. The divergence of F is going to be, so we take the del operator and we dot it with our vector field. Right, so our del operator is d dx, d dy, d dz. And we dot that with our vector field. So that's a function, but it's a vector, each of whose components are functions. So F1, F2, F3. So dot product, you multiply each component, corresponding component together, and add everything up. So d dx times F1 is the partial of F1 with respect to x. D dy times F2 is the partial of F2 with respect to y. And d dz times F3 is the partial of F3 with respect to z. So that's the gradient of f, del dot f. So remember, just like the dot product of two vectors gives a scalar, the divergence of a vector field is going to be the dot product of two vectors, and that's going to give a scalar function. So when I say scalar function, I mean it spits out a scalar, right? The normal thing we've been integrating in the past section and taking partial derivatives of. So function of x, y, and z. So just a normal function of three variables that we've been dealing with. Okay, so for example, Suppose our vector field is, and also I want to mention, so this is a definition for a vector field on R3. Obviously, for a vector field on R2, so if F is F1, F2, then the divergence of F is the same thing, del dot F, but now del is just d dx dy. So that's going to be the partial of F1 with respect to x plus the partial of F2 with respect to y. So there's no differentiation with respect to z we need to do because it's just a function. Each component is just a function of two variables. Okay, so for example, if our vector field is e to the xy, xy, z to the 4, let's calculate the divergence which we often write as div of f at the point 1, 0, 2. Okay, so we're just going to take the divergence of f at a point x, y, z, and then we're going to plug in x equals 1, y equals 0, z equals 2. The divergence of f is just del dot f. And I'll just write it out again, but you'll get in the habit of being able to do this without having to write this down. So we're dotting that with our vector field, e to the xy, xy, z to the 4. Okay. So d dx times e to the xy, what's the partial of e to the xy with respect to x?
Just a quick question.
Sure.
So when we're multiplying these together, right? So we have the gradient here, and then we're just multiplying it by its original function here, e to the xy. Is that what that is?
Right. So we're treating each of these like vectors. For the first vector, each entry is an operator, right? Differentiation. And the second, each component is a function of 3 variables. And when you multiply an operator times a function, you get differentiation, partial differentiation, depending on whatever the operator is. So d dx times e to the xy, multiplying the components together, you get the partial of e to the xy with respect to x. Does that make sense?
Yes, thanks.
Right. And right, we get y e to the xy. So that's d dx times e to the xy. How about d dy times xy? Well, we get the partial of xy with respect to y, which of course is x. I'll just write this down real quick. So that's d dx times e to the xy. This is d dy times xy. And then the partial of d dz times e to the 4. So the partial of z to the 4 with respect to z is 4z cubed. So this is the gradient of f, the vector field f, for just any point x, y, z. And then plugging in the point 1, 0, 2, just replace x with 1, y with 0, z with 2. We get 0 e to the 0, which is 0, x just becomes 1. And 4z cubed becomes 4 times 2 cubed, 4 times 8, which is 32. We get 33. So the divergence of f is a scalar function, right? So when you plug in a point, you should get a scalar, a number. The gradient of f, remember, is a vector. In fact, it's a vector field. They're important vector fields, as we'll see later. And when you plug in a point there, you should get a vector.
Wait, I'm sorry. What did you say? Like the triangle is called again? Like next to
Oh, just del.
yeah, del.
Yeah.
For del, is it always just going to be the partial with respect to x, y, and z? Like
Yeah. So if we're in R2, it's d dx d dy, and if we're in R3, it's d dx d dy d dz.
right. Okay. Thank you.
The value of 33. So they explain it in the book a bit, what divergence means. It has to do with the book would do a better job of explaining this than I could right now in a couple of minutes. But it has to do with so if you think of like the say the velocity of like gas or whatever. So you have gas, and at each point you look at the velocity of the molecules in this gas. So if the divergence is positive at a point, you can think of it as there being like outflow of gas at that point, and it's like a source. And if divergence is negative, we can think of it as it being a sink. So gas is kind of, the molecules are kind of tending to move in towards that point. It's like a sink. Yeah, I would check out Wikipedia for that if you wanted to see what it means graphically. But yeah, it's essentially measuring that kind of thing. Anything else? Cool. If not, then we will pick this up again tomorrow, and we're going to look at curl vector field. Yeah. All right. Have a or sorry, Wednesday. Yeah. Have a great rest of your day, and see you guys on Wednesday. No, wait. What is today? Oh my goodness, today's Wednesday. See you on Thursday, tomorrow. Yes. All right. When do I think the test will be graded? If we get the key, then I'm going to try to grade on Thursday. I'm going to try to grade tomorrow if we get the key in time. If we don't, then I'll probably be grading over the weekend. Yeah, but yeah, gonna shoot for tomorrow. All right, have a good rest of your day, guys.